All right, so tonight we're talking about alternating current, and there's a kind of long list of what we're talking about tonight. Some of them are pretty short topics. We're going to be talking about just in general what alternating current is and how we're going to describe it using phasor diagrams. We'll describe what a phasor is and how it works, and then we'll talk about what are called root mean square or RMS values, and then we'll kind of go through talking about what happens when you put each of the individual components, like a resistor, an inductor, or a capacitor, into an AC circuit. And then we'll talk about what happens when you put them all together into an LRC circuit, and then talk about power, resonance, and transformers. We probably won't get to these last two topics, but we'll talk about those on Thursday night. But the rest of the stuff we should be able to get through it. I'd like to, at the very least, get to the point where we can talk about LRC circuits and how they work with alternating current, as well as be able to do some problems to show you how they're used. Alternating current is... I think it's one of the things in this class where the theory is much harder than the actual problems. The problems are, I think you'll find the problems are really easy, actually, because once we go through and learn kind of all the details about how alternating current works, you're going to find out that it ends up, the way we analyze it ends up being really similar to DC circuits. And if you'll remember with DC circuits, okay, that stands for direct current. With DC circuits, the problems were, they're pretty easy because you just ended up doing these things with like loop rules and Kirchhoff's laws, and you kind of had these algorithms for how you'd solve them. And these are really similar, although we're not going to be using Kirchhoff's laws or anything like that for this. Okay, so let's get started. We're going to say in general that we can describe an alternating current source to have kind of, it's going to look like this. It's going to be a little circle connected to a wire, and there's just going to be a little kind of miniature sine wave inside of there. That's going to be what we call an AC source. And for the ones that we're going to talk about today, for example, if you were to go and, let's say, measure the voltage across this source, instead of getting kind of a consistent flow of, let's say, 5 amps or, a battery that has a voltage of 9 volts or something like that, what we have here instead is you have kind of a voltage as a function of time. And so we use kind of a small v to represent the voltage since it's instantaneous voltage, and this is going to be end up being equal to some kind of maximum voltage, and then you're going to have some kind of cosine function here or something like this. And the current then flowing in your circuit in certain situations might look kind of similar. Your current as a function of time might then be equal to some kind of max current also multiplied by a cosine of omega t. Now, it's going to depend on kind of different systems within the circuit, how the voltage and the current are related to each other, and we'll get into that. But within this source, you've got some kind of frequency, and it makes it so that the voltage is a function of time. If you were to plot it, if you plot voltage as a function of time, it's just going to look like a sine wave, right? And it'll continue. And you might kind of wonder, why would you want to produce or use current like this? And there's a lot of answers to that. One of the simplest answers is that this is the easiest type of current to produce. If you take the kind of basic knowledge we have of how Faraday's law works, the idea that if you take a coil of wire and you move it near a magnet, that you can induce current in it. If you take that coil of wire and you rotate it near a magnet, then this is the type of current it produces. This is the type of voltage it's going to produce for you. So it's very easy to produce, and it's also very easy to send over large ranges. And we really can't say the reason for all these things until we get to the very last topic here of transformers. But I'll just say this way, that alternating current works really well with transformers, and it's one of the main reasons that we can produce power in very distant locations and then pump it. We can pump that electrical power to wherever we want. And a good example of that is right here in Southern California, that we get a decent amount of power from the Hoover Dam. And if any of you have driven to Las Vegas, you'll know that it's not close. And that power that is produced at the Hoover Dam is sent over transmission lines, and it's done so at really low current, so that you lose less energy in the process. And then when it gets to your house, there's a thing called a transformer. This is basically the last topic here. And that transformer will basically step that current back up to a really high value that you can use in your home. So kind of getting way ahead of myself here, but it's good to understand the big picture of where we're going and some of the values of alternating current and why it's worth studying. But I will say that regardless of all those things, alternating current is the primary way in which power is delivered to your home. If you plug anything into your wall socket, you're going to be getting alternating current out of that wall socket. The frequency that you get is related to this variable here that shows up omega. So the frequency, for example, in the United States of the current that you get, so in the United States, the frequency, which is equal to the angular frequency that shows up in here, divided by 2 pi, is equal to, does anyone know what it is? In the United States, the frequency of the rate at which these fluctuations are happening in the current in the United States, you want to know what it is? 60 hertz, that's right. You'll notice if you look closely at any kind of electrical device that there's probably going to be, yeah, exactly, 50 hertz. And the other portion of this is that the V that you get at this in our country is going to be like 110 volts, 120 volts, except it's not going to be this V. It's going to be something else. Yeah, so you'd have this frequency at about what's going to be called, I'll give you the RMS value because that's going to be what matters, at an RMS voltage that's about 120 volts. And then in other countries, like the rest of the world, you get a frequency that is about 50 hertz, and you get a voltage, what we call the RMS voltage, which I'll explain in a second for these, which is about 220 volts. I think it's 240 actually, but 220, 240, somewhere in that range. This one might be 110, you might see, depending on just different regions of the country or something like that. There's a question in the chat that says, is there a reason why 60 hertz is our standard? I don't know. That's a really good question. Maybe you could go read about it. Many Irish thinks it's historical. It's probably true. I don't really know why it's different in our country than it is in other countries. 60 hertz, nice roundabout number, 60 cycles per second. That means that it oscillates, 60 times every second or 3,600 times every minute. And, our time standards are done in 60s, right? There's 60 seconds in a minute. There's 60 minutes in an hour. May have something to do with that. Our degree systems go by 60s. There's 360 degrees in the circle, and 60 degrees is the angle we use for. So I was just saying it's why Japan has 2 different frequencies, because the power generators are made in different areas at different times. Now that makes a lot of sense. Yeah. And then once you've built those power generators, even if it was a long time ago, they're still going to generate power pretty well for you. There's probably not a lot of economic reasons to. So the next question is, if you hooked up a light bulb to AC current, would the intensity be fluctuating like the way? It'd be doing so, but it'd be going at such a quick rate that you wouldn't be able to notice it, basically. And what's more important to understand is that the power output from the light bulb, it really, you get energy from a light bulb whether the current flows left or right, Does that make sense? It doesn't matter which way the current's flowing through that little resistor inside the light bulb. It's automatically going to send stuff off. But I suspect that if you got a high enough frequency camera that had a shutter speed where you could take a video of an American light bulb, you might see a temporary fluctuation in power. But something that's important to understand about that is that part of the reason why the light bulb is giving off energy is because it's hot. And just because the current flowing in the wire is going left and right doesn't mean that the light bulb is technically cooling off instantly. You know what I mean? It's the same reason why if you put your skillet onto a stove and you heat it up, right? Once it's hot, it doesn't just instantly cool off, right? So yeah. I mean, another example that may be more relevant to a light bulb would be if you take a hot poker and you stick it in a fireplace. Maybe this isn't a good example for Southern California, but if you take a piece of wire, any kind of metal, and you put it into fire, the wire will tend to glow in some way, and when you pull it out of the fire, it'll continue to glow, right? So my guess is that you probably wouldn't be able to really see the fluctuation of the light, but you can with the multimeter. You could measure the fluctuation of current, if that makes any sense. It's just that the current and the light, there's going to be kind of a time lag to where as long as the current is still going in that light bulb, it's going to light up just like you want it to. But anyway, okay, so that's a good thing to point out, though, about the light bulb, because after all, some of the things we've talked about in this class, you might think that the way that they work might be different with alternating current, but it turns out that most things operate pretty much the same. The biggest differences that we're going to see are going to occur are with the way that inductors and capacitors interact with with this, and that's going to have an impact on the way in which we can produce like high and low frequency sounds with speakers. The difference between like a subwoofer that produces really low bass sounds and a something that produces like more higher treble sounds, like the smaller speakers that you see. So we'll have some kind of understanding about why that works, and it turns out that it's related to things that you already know about, inductors and capacitors. Okay, so let's introduce this idea of phasor diagrams as a way to talk about this now. We're going to be using this constantly throughout the rest of the class, and so I'm just going to explain them. They're really just another mathematical tool that we use to describe different things, and really it has to be something that has wave-like properties, and this is obviously something that's got wave-like properties, so it's a good thing to use phasors for. Other places that they show up in physics, I know, are in quantum mechanics. I remember watching old videos of Richard Feynman, and the way he would describe quantum mechanics was by using exactly what we're about to talk about, these little phasors, these little arrows that spin around in space. It's a really kind of powerful tool that we can use to describe just different things. I guess I want to do this one. I hate that when I do this it becomes so large, but that's okay. We'll just do it like this. Okay, so you need a coordinate system. The coordinate system is interesting. It doesn't really have proper axes. We could call this the x-axis and the y-axis if we want to, but they're utterly meaningless, because what we care about here more is that within this space, what we do is we basically have an arrow. Oh boy, I just popped that arrow right in there, didn't I? That was interesting. We've got an arrow, and then the switch is off, right? Okay, shapes, arrow. Hey, that actually snapped right to the origin, didn't it? That's great. Okay, so let's use this one. Make it just a little bit longer so we can do some geometry with it. That's fine. Okay, so this is the idea. The length of my arrow here, okay, the length of my arrow, I'm going to say is I. And, just to be more clear about what I mean by this, let's indicate that we're going to call this I max, and we're going to call this V max right here. So let's go ahead and indicate that this is the maximum value that my current can have. Now you might notice with our definition of what the current here is that our current is given by a cosine of omega t. And what we can do here is we can imagine that we can represent that current by a little arrow that goes in circles. Okay, and the name of this arrow is going to be a phasor. It's a phasor because it is unlike the phasors of Star Trek, which shoot people with laser beams. A phasor that we talk about in physics is really just an arrow that kind of just goes around in circles like this. And we know how fast it goes because in order to sync up with this definition of current, what we would do is we'd say that the angle that's made with our horizontal axis right here is omega times t. And then what you can do is you can basically just take a projection. The projection of this down onto the x-axis would be our current as a function of time. So we draw a little line right here, and we say that the length of that phasor, according to just straight trig, right, would be I max times the cosine of omega t. That's just basic, trig or components, or however you want to think about it. So then the current as a function of time will always be read out here on the x-axis as the cosine of omega t. And that's what a phasor is. We just imagine that this thing just keeps going around in circles and circles and circles. It goes at a frequency that's given by this, right? 60 hertz or omega over 2 pi, whatever the radians per second is. If it was 2 pi radians per second, our phasor would start down here on the x-axis, and then it would just kind of go around in a circle. And the projection that it makes onto the x-axis is the current at a moment in time. And that's it. Does that make sense? Anyone have any questions? What we're going to be seeing by looking at resistors, inductors, and capacitors is that there's going to be a relationship between the current phasor and the voltage phasor. Okay? And that's going to be the key to understanding the way that LRC circuits work. In the case of resistors, the current phasor and the voltage phasor are going to kind of line up with each other. For resistors and capacitors, they're going to be either ahead or behind by 90 degrees. Okay? And that's what we're going to see as we kind of go through this. All right, any questions about that? Okay, now as we're describing these things, you might ask the question, okay, how do I define what voltage is in a system like this? Okay, Nathan asks, the red arrow and the green arrow look like different lengths. Does the phasor circling around not have a constant length? The phasor does, right? And they do have different lengths, absolutely. The arrow here that's labeled as Imax has a length of Imax. This arrow that represents the current on the bottom right here, at any moment in time, represents the current at that time, which will always be less than Imax, right? Does that make sense? So the circle that's moving around is constant length, but when you take the cosine of the angle, I mean, for example, what would the value of the current be when the phasor is pointing straight up this way? What would the value of the current be then? And remember, the current is basically just a projection down onto the x-axis. No, you don't have to change it to a sine, no. So the idea is that at any moment in time, you basically just drop a line like this. So if I had a system, if Imax was pointing straight up like this, and I take the cosine of the angle, well, the angle's 90 degrees, so you get the current at that moment in time is 0, right? If you then let the phasor rotate around until it's pointing this way, you're going to get negative Imax, and then you'll get 0 when it gets back to here, and you'll get back to positive Imax when it gets back to here. The distance from the x-axis, yeah. The green little arrow. Yeah, not the distance from the center, that's right. It's making a circle. Yeah, it sweeps out a circle, that's right. And it sweeps out a circle at a rate of whatever omega is. So you can imagine if it was 2 pi, it would go around once every second, right? Once every second. If omega was 4 pi, the phasor would go around twice every second. And the projection that it makes down here on this horizontal axis, or if you want to call it the x-axis, that's fine, will always give you the current at that moment in time. All right, let's switch gears a little bit. We'll keep using these phasors, so if you're a little confused as to what's going on here, don't worry about it. We'll keep using them, and hopefully you'll get kind of a picture. Okay, so the next thing we want to talk about are what are called root mean square values. A natural thing to ask would be, okay, well, if I have a voltage that's oscillating in time, right, then how can it be the case that when I read information about America, I find that you get 120 or 120 volts out of the wall socket? And what that really represents is what's called a root mean square value. If you think about the way that this voltage is occurring, it's oscillating in time, right? It's oscillating in time. So at any moment in time, if you want to describe what the voltage is, that's not a very useful piece of information, right? Exactly what the voltage is here, or what the voltage is here, or what the voltage is here. It's not particularly useful to know exactly what that value would be at each of those moments, right? What's more relevant is kind of on average, how much voltage are you getting out of your system right here, and that's where the root mean square comes about, okay? So the way that we're going to define this root mean square, I don't know if this is a topic so we talked about this in my 1B class, right? This is something that comes up in 1B because we talk about root mean square velocities, so you may have seen that there. But the idea of a root mean square is basically that you just take your current and you square it, and then you average it, and then you take the square root of that. And it might look like, okay, I'm squaring something and then I take the square root, but the key thing here is you average it first. And so the effect that has is that even though the current at a moment in time might be negative, you're going to square it, right? And then you average all the squares together. And that's what we call the root mean square. All right. So what's that going to look like in this case? We can actually work it out because we know if current is a function of time is given as basically this Imax multiplied by the cosine of omega t. We could use cosine or sine here. It doesn't really matter. Then if we square this function, that's really easy to do. So I squared is going to be the current squared, the maximum current in the system squared, multiplied by cosine squared of omega t. And now really what we want to do is we want to average this function. There's different ways we can do this, but they all amount to doing the same thing. The way we'll do it here is we're just going to say that we know something about cosine squared, right? We know that we can use the identity here to simplify cosine squared. If I have cosine squared of theta, for example, this is the one that's equal to the 1/2 and then 1 plus the double cosine angle. Yeah, whether you remember that or not, I don't know, but I'm sure you've all seen this at some point in time. So if we use this identity on our function over here to the left, then we can write it out as... So the whole thing's multiplied by Imax squared. So we're going to end up getting something like 1/2 Imax squared plus 1/2 Imax squared cosine squared of omega t. And then we have to average this, right? So now what we have to do is we have to take this entire thing right here, and we need to average it. Now, what does it mean to average one of these functions? Well, there's mathematical ways you can do this with calculus, right? You can basically integrate over one period if you want to, and then divide by the period. That's one way to average a function. But this one's even easier. We can figure this out. Oh, whoops! I made a mistake here. That 2's in the wrong place, isn't it? Oops. This should be cosine of 2 omega t. There we go. Cosine of 2 omega t. So when we say we want to average that, we kind of think about what's represented by this. And this part in particular right here, isn't the average half the amplitude? That is not true. The average is not half the amplitude. Wait. Maybe in certain situations, maybe? In this case, actually, it will be yes. In this case, it's going to be half the amplitude, yes. Yes, that's right, Ash. I don't know if that's always true, is it? So the cosine of 2 omega t, for any sinusoidal, okay, yeah, for any sinusoidal function, I would agree, that makes sense. Okay, so cosine 2 omega t, what does that look like? Well, that's just a cosine function, right? This would be cosine of 2 omega t. It's not exactly, sorry, that looks awful. I should really have my, whatever. It's an oscillating function regardless of where you put the axes, right? I don't want to confuse you. I'll be right. I'll do this right. Okay, cosine of 2 omega t is going to look something like this. There we go. The point is that if you average over one cycle for a cosine function, right, half the time it's above the axis, so it's positive. Half the time it's below the axis. And so what that means is if you average over one cycle, you basically get 0. So when we do this averaging process here, what we find is that if I do I squared and I average that, what I get is 1/2 of Imax squared. But we're not done because the last step we need to do is to take the square root. So if we take the square root of both sides, then what we'll have is the RMS. And so this is our definition of RMS current, root mean square current. It's just equal to, this is really simple, you take the square root of Imax squared, that's just going to be Imax. And then we just need to divide that by square root 2. And we could use this value if we want to here to kind of, say something else. The RMS voltage is going to look the same. VRMS is going to be Vmax divided by square root 2. And we could use it to take a value. For example, if we say that VRMS in America is 120 volts, we could ask the question, what is Vmax going to be in the United States? And according to this equation down here, you have to take the square root of 2, and you have to multiply that by VRMS. And then what you're going to get, I think, is like 170 something, right? You take 120, and you multiply it by that. $170 almost exactly. So this is your peak-to-peak voltage, so to speak, in America would be 170. But if you were to get a device such as a multimeter out and you put it on the proper settings, then you'd actually measure 120. Because as it turns out, we design our voltmeters to be able to measure AC current, and what they end up measuring is the RMS value. So if you were to go take a standard multimeter, set it to the alternating current version, which, if you're interested, it looks like this. The DC version looks like this. Straight line for DC, wavy line for voltage. So this is a setting on a multimeter. If you were to go into your multimeter and just plug it into your wall socket, what it would read out would be something between 110 and 120 volts. Okay, so we're kind of defining definitions here. And again, like I said at the beginning, the hardest part about what we're doing tonight is the theory. So if you get lost at all, please feel free to ask questions. But so far we defined what a phasor is. We've defined the way that the current is going to flow from our source. And we've defined what a root mean square measurement is. Okay. Does anyone have any questions? Oh, I'm sorry. Yeah, my bad. Yep, that's Vmax. Thank you for noticing that. I'm sorry, that's confusing. Yeah, 170 is going to be the Vmax. Okay. So, the first thing to talk about is, so we did 1 and 2 here. The next thing is going to be resistors and AC current. I thought I moved this over far enough. Maybe I zoomed in too far. All right. So we're going to look at what happens when we do the following. We're going to put just a resistor we're going to connect it up to an AC current source. This is by far the simplest of the ones that we'll consider today. So what this will look like is we're going to have an AC voltage source. So we have AC voltage. And that's, again, it looks like this. It's the symbol you're going to see for it. The little sine wave helps you remember what that is. And we're just going to connect that up to a resistor. And we're going to say that our current is flowing in our circuit like this at a moment in time. We have a resistance in the circuit that we're going to categorize as R. And again, we're going to start off with the idea that the current as a function of time flowing in our circuit is going to be given by, just in order to kind of save time and also make things neater, I'm going to use just I to represent Imax. So if I just write I, I'm going to mean Imax from now on. Okay, so this I here is going to correspond to the max current. But I'm just going to assume that you know that. If I want to write RMS current, if I'm explicitly talking about RMS current, I'll write RMS right here. All right. So if we want to think about what the voltage across our resistor is, right? If I want to know, for example, if I connect a voltmeter up between A and B, what it would read, well, we already know that there's a relationship that tells us that if I know what the current is in my circuit, what do I need to multiply that by to get the voltage? Yeah, I times R, right? So that means that my voltage in my circuit is really just going to be the current here, which is I times R times the cosine of omega t. What this tells me, and I'm going to write this another way just because it's going to be consistent with what we're going to see show up here later. I'm going to call that right there just VR, big VR. That's what IR is going to be, cosine omega t. All right, where VR, the voltage across my resistor, it's exactly what it was before when we talked about AC circuits. But we're going to have a definition of what the voltage across an inductor and a capacitor is. We're just going to kind of be consistent right there. Okay, what we notice is that the current is cosine omega t. The voltage is cosine omega t. So we basically say that the current and the voltage are in phase. They're in phase. The voltage across the inductor and the current across the inductor are in phase. That means that when the voltage is pushing to the right, the current pushes to the right. When the current is being pushed to the left, the voltage is to the left, and so on and so forth. And if you think of the voltage as being the cause of the current, then the idea would be that when the voltage between B and A is such that B is higher than A, current goes left. If the voltage at A is higher than B, current goes right. Pretty simple, right? So the current in this system, the way it's going to be flowing is it's going to flow to the right, and then it'll drop to 0, and then it'll flow back to the left, and then it'll drop to 0, then it'll flow back to the right, and it'll just repeat that set, back and forth, just oscillating back and forth, just as you would expect. And the current will always kind of be in phase with the applied voltage. Okay? Now, if we draw that on a phasor, the phasor diagram the way that would look would be we'd come in here, we would draw a phasor for each of these. So we're going to have one phasor to represent the current. Let's use this for that. I'm going to have to click this again, I'm sure. So we'll have one phasor for my current. It's going to point like that. So that's going to be my current phasor. Okay. that current phasor is going to oscillate around in a circle, always making an angle right here that we call omega times t. And then right on top of that, I'm going to draw my voltage. Now let's say that we have a resistor that's like 0.5 ohms or something. In that case, the voltage phasor would end up being right on top, but just smaller. Right there. And that's going to have a length that we call V, right? And then what we do is we basically just drop a line down here, and we'll draw a phasor this way, and say this is going to be my voltage as a function of time. That's going to be my voltage across my resistor as a function of time. And for the current, we would do the same thing. The current phasor, just kind of draw it beneath this here, would go this way, and that's going to represent the current as a function of time. And both of them would be going around in a circle. Yeah, and we know to put them in... That's right. So Ash says, and you know to put them on one another because they are in phase. That's exactly right. Yep. They are in phase with each other. Now, one thing that you're going to notice as we go forward, the x-axis is always going to look the same. Kind of. You're always... And on the x-axis, they're either always going to be kind of on top of each other or something like that. But this is the only case that we're going to see today where the current and the voltage phasors are in phase. Okay? It's the only case where they're in phase with each other. The other two, they're not going to be in phase. And we could go a little bit farther with this here. We could, for example, do a plot if we wanted to. I guess that would be like this. So if I want to do a plot of the way that this works, then I would say, well, they're in phase with each other and they're both cosine functions, right? So if I want to plot like here, let's use the same colors as we did on the graph over there. So if I want to plot the current up here as a function of time, well, it's going to look like, just your standard cosine function. And if I want to plot my voltage on the same graph, also as a function of time, it is going to be like this, also a cosine function that is completely and totally in phase with the other one. Okay. All right. Applied voltage and the current are in phase. This is like a scenario where imagine that you're pushing a child on a swing, and imagine that the rate at which you push the child is like the voltage, and the kinetic energy or the velocity of the child is like the current. Then this is synonymous with the way that that would work, right? Think of the voltage as force and think of the current as velocity. If your force that you apply to the child as they're swinging is such that you always push them when they're at the bottom and when they're going in the same direction, and then when they come back down, you push them back the opposite way, then that's kind of consistent with what's happening here. And that's because the resistor is kind of just this passive element that dissipates energy. So as long as you're pushing the current to the left, it goes left. If you push the current to the right, it goes right. That's not going to be true for the inductor and the capacitor. All right. How do you know the magnitude of I is larger than V? It doesn't necessarily have to. In this case, you could say that, well, if I look at the length of I and I look at the length of V, I could actually figure out exactly what... oops, that's backwards. If I look at the length of I and V here, it really just tells me that if I take V over I, that's equal to my resistance, right? So in this case, it looks like R is maybe, at least on my picture right here, R would be on the order of maybe 0.75 ohms, right? But if the resistance had a value of like 1,000 ohms, then my voltage phasor would be 1,000 times longer than my current phasor, right? So this is just for instructional purposes, but good question. Ty, do you have a question that you're typing out? Oh, wait. You can't compare B to I. They are in different units, but I mean, you can. I mean, there's nothing that stops you on a diagram from... I mean, you're not wrong. They are in different units, absolutely. But there's nothing that's stopping you on a diagram of drawing it to scale, right? In terms of the size of the things. But you're not wrong. They are different units. Absolutely. Very good point. And whatever scale you've drawn is going to depend on how you've decided to make those units. I'll tell you how you could do it, by the way, is if you plotted, instead of plotting I, but instead you plotted, here, what's a better way of writing this? One way you could do it is by making the dimensionless, right? So if I plotted the current divided by the maximum current, and if I plotted the voltage divided by the maximum voltage, then you could definitely, there would be some meaning, right? Because then you kind of eliminate the units, right? So, all right. So let's keep going. We could do a problem here, but I really don't think it's very useful. Oh yeah, we don't have a problem for the resistor one. I do have a problem for the inductor one, but I don't think we'll do it. Okay, so next we do inductors. And we're going to talk about pure inductors, which means that they have no resistance. This is, of course, totally unrealistic based on modern technology, but who knows? Someday maybe superconductors are going to be easy to find. Okay, so an inductor in an AC circuit will look similar to what we just saw. We will have our voltage source right here, connected up to an inductor. So there's our inductor. Our voltage source is going to have current that flows out of it, just as we said before. And what we're interested in figuring out here is kind of what is the voltage across our inductor. That's what we want to look like. Okay? And so let's say that at a moment in time that the current that's coming out of the source has a magnitude of I, and it flows through our inductor. Just to remind you again, an inductor is basically just a bunch of coils of wire designed to kind of maximize Faraday's law. And we know that for an inductor, we have this relationship that the EMF across an inductor is equal to the negative of L times the time rate of change of the current, right? But for this here, we're going to be interested in finding the voltage across the inductor. And what I would argue, and your book tries to do so as well, would be that the voltage that I actually measure across my inductor is always going to kind of be opposite to this. Like if the current's flowing to the right, that voltage might kind of point back to the left. The main thing here we're going to do though is we're just going to do positive dIdt to describe this. And I would highly encourage you, if you want to read about it, to go read about it in the textbook. I'm not going to spend a lot of time in class talking about why we're going to write the voltage across the inductor as positive. I'm just going to say that there's a long description in the textbook that will confuse the hell out of you if you want to go read it. And I have no intention of trying to repeat it to you. I just know that we kind of know what the right answer is as often in these cases, and so we're going to kind of stick with it here. So the voltage across our inductor, we want to do dIdt, the derivative of this term at the top, right? And that's easy enough to do. I take the derivative of the cosine function. I'm going to get negative. The I is in the front. We pull the omega out in the front. And then we have to multiply by L. Okay. The negative sign came from the derivative. And then we would get sine of omega t. That would be my voltage across my inductor. Now, in order to kind of make more sense out of this, we're going to use a trig identity. So we're going to use the identity that if I have the negative of the sine of theta, that's equal to cosine of theta plus 90, or pi over 2, however you want to put it. So negative sine of theta is equal to basically theta plus, we'll do pi over 2, because your book uses 90, but everything in this situation is going to be done in radians, so I think it makes more sense to put it as pi over 2. But regardless, okay, so when we change that around, then we get that the voltage across our inductor as a function of time is going to be equal to I omega L multiplied by the cosine of omega t, and then we need to add a pi over 2 like that. Now, what that means in terms of what that's going to look like on a phasor diagram is that the current is just cosine omega t, but the voltage is cosine omega t plus pi over 2. So when we draw that on a phasor diagram to get a feeling for what that looks like, then we will start off by drawing an arrow for our current again. So our current on the last diagram, I think we used red, so we'll do that again. Okay, so that's going to be my current phasor. And then the current phasor needs to have an angle right here, that's omega t. And now if I drop in my voltage phasor, did I switch colors on you guys? Yeah, I kind of did. Hopefully it's not too confusing. My voltage phasor is going to have to be at right angles to that. Okay, shift a little bit there. I think that looks like roughly a right angle. So this needs to be a right angle here, so that the total angle that's made from here all the way up to here, that whole angle is going to be, oh, look at that. That ink to shape thing really kind of messed that one up. Turn that off. That whole angle would then be omega t plus pi over 2. Right? And that's going to be my voltage phasor. Now, according to these equations, the current phasor tells me that they're rotating in the same direction. Yep. The rate at which they rotate is given by omega, and the voltage phasor is always going to be at least 90 degrees ahead, basically, so that we can say that VL leads the current by 90 degrees. We use 90 degrees when we say it here, but just remember that in the equation, we'd have to put pi over 2, right? There's kind of a mnemonic for this, which is, you write as ELI, and the mnemonic is that the EMF leads the current, and the L here is a reference to the fact that it's an inductor. Okay, that E leads I, Eli. So that's in a pure inductive circuit, pure inductive, right? Okay, now we've got this definition of what the voltage is right here, but we can say something more about it. And let's do that. So my voltage is a function of time. I could rewrite it like this. In the previous one, I just said that it was kind of VR. I'll call this one VL like this. And then say that's cosine of omega t plus pi over 2. And so we're basically going to define the voltage across my inductor in one of these circuits to be equal to current multiplied by omega times L. And then you look at this equation and you kind of think about what we just did. A second ago, what we just said was the voltage across my resistor was I times R. And you kind of compare these two terms right here and you think, wow, they're really similar. In fact, this whole thing, omega times L, actually has to have exactly the same units as R, right? It has to have the units of resistance. And if you work it out, it does, because 1 Henry, which is the measurement for inductance, is equal to 1 ohm times a second. This is something that came up in a previous chapter when we were doing things. We noticed that 1 Henry actually has the units of ohm seconds. So if you multiply by omega, which has units of inverse seconds, well, then those cancel out and you actually get units of ohms. So what we're going to do is we're going to define omega L, okay? We're going to define that to be X sub L, so it's a capital X with a L subscript on it. And this is going to be called inductive reactance. Inductive reactance. And this allows us to rewrite the VL equation to give us something. So this is something really important to remember. Okay, this is our first equation that we're getting at. This is something that's new here. Inductive reactance is defined as omega times L. And so the big thing to take away from this now is that VL, the voltage across our inductor, is going to be equal to, and this is kind of the maximum voltage across the inductor, the current multiplied by XL. And if we rewrite it in a different way, then we can see that what this inductive reactance tells us is the larger that it is, Well, what's going to happen? Let's say that you knew that VL, let's say, was 170 volts, like it is here in the United States. Let's say VL was 170 volts. And I told you that XL was 17 volts. What would the current be? Oh, sorry, 17 ohms. What would the current be? If this is 170 and I tell you this is 17 ohms, what would the current be? It'd be 10, right? And then what if I increase this to 170 ohms? I get 1 amp, right? Very simply put, the larger the value of the inductive reactance, the bigger the current's going to be, right? Sorry, the larger the value of the inductive reactance, the smaller the current's going to be. So, inductors are these complicated objects, right? They're these very complicated objects. They do these things where they kind of inhibit the spikes in current. They can store energy in their magnetic fields. They're these coils of wire, right? But when they're placed into an AC circuit, what they do is they tend to reduce the current, which, if you think about it, is exactly what a resistor does, right? It's exactly what a resistor does. The bigger the resistance, the smaller the current you get, right? So when placed in an AC circuit, an inductor acts very similar to the way that an inductor does. Sorry, resistors and inductors act very similar to each other, as long as you remember that to find the quote kind of resist. This is like the resistance of an inductor. It's not. That's not what it is. It's inductive reactance, but it shows the way that the system reacts to the inductor, right? And if we write it like this, okay, and now we start thinking about what the omega does. High frequency. What's that going to do to the current? If the frequency is really high, this is going to be small current or big current. It's going to decrease the current, right? So this is going to have small current. And if you have low frequency, well, that's going to give you a big current, right? Now, does that make any sense? These are inductors after all, right? And what it's saying is that if the frequency is really high, you're going to get a very small current. Why would that be the case? Why would it be the case that if I have something like an inductor and the frequency of oscillations within the circuit is really high, why would that affect the outcoming current? Okay, so Meower says because they're storing energy and they have to resist the change in the current, the switching frequency. Yeah, they resist the change. That's exactly right. So the bigger the change, which means the frequency, right? The frequency is literally the rate of change of the current, right? It's the rate at which the current is changing. So the bigger that is, the more that the inductor does, the more that the inductor reacts to what's happening in the system. However, if the frequency is really low, then the inductor is not going to do as much. It's not going to have nearly as big of an impact. It's not going to have nearly as big of the back EMFs that these inductors produce whenever you have really high frequency. Because after all, the inductor is it's like adding mass to your circuit, and if it's high frequency, then that's like taking a piece of, this is a really simple experiment you can do yourself. You pick up something that's really light, right, and you try to shake it back and forth, it's easy. But if you pick up something that's really heavy like a rock and hold it in your hand and try to shake it back and forth, you'll notice that it's really hard to shake it back and forth very quickly. And that's because of not the weight, but the inertia of the rock. And this is kind of the same idea. So one thing that can be said about inductors is they're kind of like, they have the effect of allowing kind of low frequencies to pass through. So it can be referred to as kind of a low-pass filter. It allows low frequencies to pass through. Because the current's small for high frequency, it's large for low frequency, and it can be used as a filter to filter out the high frequencies, allowing the low frequencies to pass through. So if you think about this in terms of the way that sound works, if you wanted to design a device that took electrical stuff, like you have in a radio, for example, or you have in a sound system, and you want to convert that energy into sound, but you want to produce low-frequency sounds, then an inductor would do that for you, right? The inductor would basically amplify the low-frequency sounds, but it would squelch out the high-frequency sounds. Does that make sense? And that's where you get those big bass sounds from those gigantic, like, subwoofers that people will put in the back of their cars, or that you have in movie theaters, or maybe, I mean, I have a subwoofer in my home that I got from Radio Shack years ago, and it pumps out just stupid amounts of bass that causes my house to shake. And it all happens because that low frequency causes the output current to be really high, and the output current is related to the sound that comes out, basically. Okay, does that make sense? Do you know what an equalizer is? If I say the word equalizer, do you know what I mean? Mr. Meowers does, but you're very technically savvy, I think, which has become pretty clear. No? Don't know what an equalizer is? I want to show you a picture of one. You've probably seen this. It's an audio thing, that's right. You've probably seen this at some point in time on equalizer. We're not talking about the Denzel film. I never saw this one. I don't know if it's any good. It's got Bill Pullman. Okay, now let's see if we do an image of this. You have a small experience. So this is an example of an equalizer right here. You guys ever seen these things? These kind of control boards? What's a simpler one? This is like a simpler one. I know on... so this... I'm pretty sure that you probably have equalizers on a lot of, audio, like, kind of things that you can download and stuff like that. It's like a soundboard. Yeah, it's kind of like a soundboard. Well, it is. A soundboard is an example of an equalizer, for sure. Yeah, maybe I should say soundboard. Maybe that's something... Look at this one. It's 43 euros. And there it is. And you'll notice if you look at this thing here, there's all these numbers up here, right? 20K, bunch of zeros. These are frequencies. And basically by manipulating these knobs, you can manipulate the sound, okay? And the way that they kind of work is they have pieces inside of them that are inductors, basically. And when you turn up the bass sounds and turn down like the treble sounds, then you get that like really deep bass. Your car might have something like this. I don't know if you all listen to the radio in your car, but a lot of cars will have a knob for bass and a knob for treble, right? All right. Okay, so Meowers says a soundboard. Here we're going to get into really some details about this. A soundboard is for mixing different inputs of sound. An equalizer manipulates the input. A soundboard can have equalizers for each channel on the global level. Yeah, that makes sense. A soundboard could also be just those kind of things that they use on radio stations where people, like, they touch a button and it plays an audio sound, like Homer Simpson saying "doh," or like some famous quote from someone or something like that. I don't know. But anyway, so the main point here is that, look, I mean, we've talked about inductors in the past, and we learned all about how they have this effect of kind of creating a back EMF. They smooth out fluctuations in current, all those kind of things. But when you put them in an AC circuit, they're actually pretty simple, because depending on what the frequency of the circuit is, right? Once you know what the inductance is, you just take that, you multiply them together, and you get this thing. And all of a sudden, you get this really simple equation that looks just like Ohm's law, right? And that's something that shows you that the way that an inductor behaves in an AC circuit is actually kind of simpler, right? It's kind of simpler than what it does in a DC circuit. The inductor, by the way, would allow DC circuit direct current to pass as well. So it's low pass filter that allows low frequency signals to pass through. Okay, does anyone have any questions? Yeah, there you go, Jesus, yeah. So if anybody has any experience with like being in someone's car where they really turned up the bass, literally at its core what's happening is the inductance of the circuit is being changed. And how that's happening could happen in various ways. Someday you all will be engineers and you'll be very good at manipulating these kind of things. But it could involve taking like a piece of iron and moving it in and out of the coil to kind of variably adjust the inductance. It could involve disconnecting certain like coils of it by some kind of a rotor or something that like kind of moved around it and only equipped like half of it, connected half of it to the circuit, anything like this. Okay. So that's a good place to stop while we take a break, and then we'll come back and talk about capacitors. Okay. So the new thing here was the inductive reactance that we introduced. X sub L is equal to omega times L. So just keep that in mind. All right, I'm going to stop the recording now.